students, other teachers. Okay. Let's see. Recording. Okay. Newton's law. You got that? I don't get what's so funny. I don't get what's so funny, seriously. Yeah. That's the correct thing to say. Why, what do you say? Okay. Maybe Andek just has good manners. Alright.
You believe God.
Ah, true. Okay. Newton's law, you got that? Yep. Good bit to do. Okay. As you know, the Earth pulls other masses to it, and the Sun pulls the planets, such as the Earth. Therefore, there must be some kind of field, like an electric field or a magnetic field. So, remember we said if this is a proton, there's a field around it. And if I bring the electron close to it, then it gets pulled in. Okay? Same with a magnetic field. Remember we drew the magnetic field lines. So there must be some kind of gravitational field that pulls things in. So suppose that there is a field, a gravitational field around the Earth and other masses too. What would it look like? Well, you won't be surprised to imagine that it looks like this. Now, just before you draw this gravitational field, these are the field lines. And of course they point in because masses get pulled in. What do you think these circles are? What did we call these? Yeah, but if you remember the lesson on the electric fields, we have these special lines. Does anyone remember what they're called?
No.
Begins with an E, EQ?
Equator.
No. No. I taught you had it. You don't remember? No? Okay. These lines are called the equipotential lines. Do you remember that? What's the meaning of an equipotential line? Do you remember? Yeah. So but think about, no wait, don't look. Think about the word, okay? What does the prefix equi mean? Equal. Equipotential. Equal potential. So the meaning is everywhere on this line you have the same potential energy. So if you're here, you have the same potential energy as somebody who's here or here. Okay? That makes sense because, if I move this off the ground, its potential energy is the same if I keep it at the same height. So these are the field lines and these are the equipotential lines. In the exam, I think I said this before, they sometimes ask you to draw the field lines and or the equipotential lines. Okay. Notice that the field points towards the centre of the Earth. Okay, so when you copy this in your book, you must write three things. The title, gravitational field. Beside these are called field lines, so write field lines. And then beside the circle, write equipotential lines. Okay? Just so you can try to remember this later.
We just read the notes on there.
Just say what?
We just read the paragraph on there.
No, just the diagram with the title here. Okay, you drew that? Yep. Okay. So, next now. It was discovered by Newton that masses attract other masses. We know this, you learned this in middle school, but it was first discovered by Newton. And he also discovered that the bigger the mass, the more force there is. Again, you learned this in middle school. So Newton was the first person to come up with this formula to calculate the force. Now if you look at this formula, it looks very similar to what other formula? It looks like coulombs, doesn't it? Except instead of a K there's a G, and instead of a Q there's an M. But the reason it's quite similar is because it's a field. It's just a gravitational field, whereas coulombs was an electric field. And also, remember I said before, this is an example of an inverse square law, which I said is quite common in physics. So, this is the force of attraction between two masses, where F is the force, M's are the masses, and the distance between their centres is R. The G is this constant, which is actually quite small. That's actually a very small constant. And the units, you could work them out, are Newton meter squared per kilogram. Write this down, and you need the G. I think the G is also on your calculator as well. Yeah, it is good, okay.
39.
39, okay. Okay, you got that? Not yet. Got that? Great, okay. Now, notice how similar this is to Coulomb's law. We've not said yet what the field strength is. So remember, the field strength in an electric field was the force per unit charge. So let's think about this. Let's try and draw a comparison. We said earlier that the electric field strength is the F over Q. The electric field strength is the force divided by the charge, Q. So what might be the field strength for a gravitational field? Well, that would be the force, but not divided by the charge, because there's no charge here. What's making the field? What causes the gravitational field to appear? It's the mass. So it's F divided by M. Okay? The letter we use for the gravitational field strength, that is how strong the field is at a distance out here, that letter is G we use for gravitational field strength. So the gravitational field strength, G, is the amount of gravitational force per unit mass in the gravitational field. So mathematically it's G equals F over M. Okay, you got that? Yeah? Okay, no problem. I'm not going anywhere. Yeah? Okay. Now, we know a formula for F. So, for example, if that's M and that's big M, then you could say that's G M M over R squared over M. So that cancels with that, and you can be left with this formula. The big M is the planet, for example, and the small m is like the person or the spaceship or whatever. So this is another way of calculating the gravitational field strength. And the units, of course, are newtons per kilogram. Newtons per kilogram. Got that? And you see it's newtons per kilogram. Now let me give you an example. Oh, sorry, do you have that, Chow? Okay. I'll give you one to calculate. So here is planet Earth. And planet Earth has a gravitational field. Now, where do you think the field is stronger? Here, here, or here? The bottom, yeah. Because as you get closer to the Earth, you get more of a gravitational pull. Let's say, here's Chow, for example. What did you say you were, Chow? 90 kilograms? Yeah. 90 kilograms, good, okay. So, we want to know what is the gravitational field strength. How strong is the field here? That's the G. Okay. So you use this formula. This M, which M is that? Is that Chow's M or the Earth's M? Good, okay, so I'll just get that mass for you. That is, for the Earth, is 5.97 times 10 to the 24 kilograms. Yep. And also, you need to know the distance from here to here. And that's the radius of the Earth, which is, I can get it here for you. Can you see this? 6378 kilometers. Can you see that okay? Yeah. So my question is, what's the G? So you have to use this formula. You know the M, you know the R, so you can calculate the G, how strong the field is. And the unit will be in newtons per meter. So what that means is, newtons per kilogram. What that means is how many newtons of force per kilogram. So for example, imagine the answer was 2. Then that means for every kilogram, there are 2 newtons of force in the gravitational field. Okay, so obviously it's useful to know this. Can you calculate this using the numbers here and using this formula? Calculate the G, please. Yeah, give me 1 decimal place is fine. 9.8. You got 9.8 as well, Stephen? Now don't forget this is kilometers. Siva?
Yep.
Are you sure? Kim? No? No? Okay, did you type, guys? Did you type this in? G equals 6.67 times 10 to the minus 11, that's the G, times the M, yeah, over the or, squared. Yeah? Okay. So, does anybody notice anything familiar about this number? Has anyone seen this number before? 9.81?
Yes, the Earth's gravity.
Yeah, which is also called the letter G, isn't it? In fact, that's not a coincidence, because another way you could have got the answer, you have a formula for weight, don't you? And that's equal to mg. And we said the gravitational field is equal to F over m, but the F is the weight, so that's mg over m. So in other words, the gravitational g and the acceleration g have the same value on the surface of the Earth. Okay, so it wasn't a coincidence, it should have been the same. Can I continue? Right. Oh, that's what we just did. Yeah, okay, so we did that. Okay, so just to recap so far, all masses produce a gravitational field which attract other masses. The force is given by Newton's formula. Fields always point towards the centre of the mass. The field around a small mass can be ignored compared to a bigger mass. So, for example, I know this seems really weird, but the Earth pulls me down, and I also pull the Earth up. But that is so small we can not consider it. But it is true. The Earth is pulling me down, and I'm also pulling the Earth up. But we kind of ignore that half. So we usually have the formula with a small m and a big M, and we don't care about the small m's pull on the big M. Yeah? Because masses are positive, the field never points out but only in. So it's always pointing in. The strength can be calculated using this formula, and in fact the acceleration due to gravity in the field is the same as 9.81. The G is about 9.81 on the surface of the Earth. Okay. So now we have to look at the potential energy formula. But before I show it to you, I want you to think about what it could be. If you look at Coulomb's lesson and the formula I gave you for potential energy, try to figure out what it might be for the gravitational field. Because if you compare the formulas, I think you can get it. So what do you think it might be? Kim, do you have the formula? You know the formula for potential energy, K, Q1, Q2 over R. What do you think the formula for potential energy is for this lesson, if you compare? So instead of a K, it's... What's the constant in G? Yeah. So G... No. G, instead of Q, it's... Yeah, so what do you think? It's G, M1, M2 over R. It's also negative. Why is it negative? Because it's trapped as well. So, you're not surprised that this is the formula for gravitational potential energy.
So
Oh, sorry.
two methods on the gravitational force. Like these two methods.
Yep. But it's so small, you would need very, very sensitive equipment to detect it. Now, they've done it before in a lab. I think they had something like a 1,000 kilogram lead weight, another 1,000 kilogram lead weight. They hung it on some very sensitive equipment, and you can't see it with your eye, but they were able to measure the tiny force attracting the two of them. Yeah. The reason the force is so small, Matt, is because this G constant is so small. It actually means that gravity is a weak force. Let me show you how it's weak. I lift this bottle up. What's pulling it down? The weight. The entire Earth is pulling this down. The whole planet is trying to pull this down, but I can pull it up. See? Gravity is quite a weak force. Imagine if the Earth was a giant magnet and this was like a piece of metal. It would break my hand. It would be so strong. Okay? So gravity is a very weak force. It's very weak compared to other forces. Okay? Right. But you might be thinking now, actually, don't we already have a formula, mgh? So we have to see, how is it that we have two different formulas? This is what I want to have a look at next. So this formula works on the surface of the Earth, but let's have a look at that. Now, this proof, the proof is not something they'll ask you on the exam, but I think it's good for you to see it and to write it down. So let's just set the picture up here. Here's the Earth, and here's a mass on it. And I move the mass up to this level. So somebody moves the mass up. According to the formula we had before, how much energy did this gain? It gained potential energy. That's equal to mgh. Yeah? But we have this new formula that says potential energy is minus g over r. So here, according to this, so let's forget about this for a moment. According to this formula, it has potential energy here and here. Which one is bigger? Which potential energy is bigger? Top or bottom? Top. Top is bigger. Because it's closer to being free and being zero. So the top is bigger. So when he moves this up, he has given this potential energy. He's moved it from this level to this level, so it's a gain. How much potential energy did it gain? Well, that would be, now let's just call that distance h. That would be minus gm over r plus h minus gm over r. Yeah? So this one's on the top and this one's on the bottom. So the change in potential energy is gm over r minus gm over r plus h. Is that okay so far? Yeah? So I'll just pause for 1 second before I continue. I'll let you write this much down. Okay? So, this equals GMM over R minus GMM over R, and then I'll write here 1 plus H over R. So do you see I took the R out from down below here. Now, if you look carefully, you'll see that this is the same as this. So what I can do is take it out. GMM over R bracket 1 minus 1 over 1 plus H over R. Yeah? Now, there's a little trick here. Let x equal minus H over R. So I can change this into GMM over R bracket 1 minus 1 over 1 minus x. Like that. Now there's a reason I'm doing that. I don't know if you remember this from maths in semester 1. I'll just go to the side for a moment, just for one moment. Does anybody remember what this equals? S infinity. Does anyone remember what this is? No? Too long ago? You've seen this, haven't you? In GP, geometric? 1 over something is correct. 1 over what? Oh, we're getting closer. It is. Yes, it is 1 over something minus R. Yes, okay. So we've gotten this far. Yes. Okay. So you can say 1 plus x squared plus dot 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 equals 1 over 1 minus x. That's what I'm going to use next. Back here, I'm going to change this into GMM over R 1 minus bracket 1 plus x squared, etc. Close bracket, close. Now, can I continue? So look, this x here, will it be big or small? Well, just think about it. What is the h? The h would be some number like you lifted 2 meters. Yeah? And what's the r? What was the r? Do you remember? What's the r? Radius of the earth. So, is x big or small? Small. In fact, it's very small. You know, this would be 1 meter over 6,000 kilometers. 6,000 kilometers is like 6 million meters, isn't it? So it's 1 over 6 million meters. That's a tiny number. What happens if you square it? Does it get bigger or smaller? It gets smaller. And if you cube it, it gets smaller again. So because the x is so small, when you square it and cube it and so on, you can ignore its value because it's so small. So we can say that this is roughly equal to GMM over R bracket 1 minus x. Yeah? Cancel, cancel. So this is equal to GMM over R minus x. That's equal to GMM over R minus H over R. That's equal to M G M over r squared h. What I've done is I've just taken the g, the m, and the r squared and put in the middle. I took the m, put in the front. I took the h and put at the back. Now, what does this equal? I gave you a formula for this today. What does this equal? Boom. Same formula. So we've shown that you get the same answer as mgh. Right? Impressive? Amazing? Not amazing? I mean, think about, like, I think it's amazing that this formula is so different to this formula, but when you're on the surface of the Earth, you get the same answer using this formula as using this formula. And we've shown it's the same. This simplifies to mgh. Yeah? Okay, well look, I think it's amazing. And it's a proof that you'll see in physics if you do it next year. It's a standard proof. Okay. So, let us prove that this formula is the same. We've just done that. Okay. Newton's law of gravity gives the size of force between two masses. This force is one of the four forces of nature. And it's also an example of an inverse square law. So, before we go on, I just want to point out how small the g is. This makes gravity a very weak force. Okay, so let's have a look at an example. What is the force between the Earth and the Moon? And the Earth's mass is this, the Moon's mass is this, and the distance between the Moon and the Earth is this. So it's just straightforward use of the formula, okay? I'll give you 1 minute to give me the answer here. It should be pretty big, obviously. Time to the... 10 to the what? It's great when you get different answers. Right, let's see. Chow. Oh, where's my calculator? I'll have to open it again. No, what number is the G on the calculator, did you say? 39?
Yes, 39.
Okay. Let's calculate here. Did you two get an answer? Oh, dang. Okay, Matt, definitely time to buy a new calculator. Right?
I might be wrong as well, sir. No, I thought it was square amount.
Ah. It's not the calculator's fault then. You got an answer yet, Siba? Yeah?
Wait, I think this is
Similar to what they got, but you got 28.
no, 31.
Oh, 31. He got 28. Did you forget the square? Oh, okay, let's see. G is number 39, you said, Chow?
Yeah, that was 39.
Okay. M1 M2 over R squared. Oh, you're all way off. Did you forget that this was kilometers? I don't think I made a mistake, did I? G. Okay, you got this. M1, M2, or squared. This is the answer. What happened, Siva? What happened for you?
I think I need to redo it.
It's okay. We can just continue. You're all sleepy, I think, is what it is. Yeah.
But we all got the same wrong answer.
Yeah. Yeah. Well, if you forgot to square it, you would get this answer.
Oh.
If you forgot to square it. And if you forgot your zeros but you squared it, you would get this answer. Yeah. Doesn't matter. Doesn't matter. Right. Next one. I think you can do this. In fact, I really hope you can do this because it's very similar to the question. Before you try it, I'll give you a hint. Do you remember that question we did with Coulomb where we calculated today the time it takes for the electron to travel around the proton? And we said, which one was it? It was question 5 in the homework. We did that one today. The way you do this one is just like the way you did number 5. So if you look at how you did number 5, I think you can do this one. So I'll give you a minute to try it. See if you can get it. Problem? Question? Are you sure? What's wrong?
No, he claims that he has the force.
Who has the force? He has the force. Well, he's the only one who did his homework, so I guess he has the force. Now, the real question, Andek, is he on the side of good or evil?
Yeah, no, which one are we?
He is wearing a lot of dark clothes. I'd be careful. Oh, and when you get your answer, if you get an answer, convert it into days, because it'll be a big answer. We're getting answers. Got an answer? Yeah? It's out of space. You crashed it. Wow. Okay. Let's see what we can get. How? Okay. I'll do it now. Did you get an answer, Andek or Chow? No answer? Matt? What answer did you get? The only question on the board. What? Oh no. Oh, so none of you have this answered, yeah? No answers for this? Your calculator, no. Kim? Oh, guys? No, okay. No. Alright. Okay. Earth. Moon. Goes around. And my question is, what's the time? So we've seen this. T equals what? 2 pi over omega. Do we know the omega? No. But we can say F equals m omega squared or. Yes? So omega is root F over m or. So this is 2 pi root m or over F. Do we know this? Yes. This, but we don't know this. But we could know it. We could know it by using the formula today. G m m over r squared. Now let me just clean this up a little bit, because what I can do is change this into 2 pi root m or cubed over g m m. So that's equal to 2 pi root r cubed over gm. And just to be clear, this one is the big one and this one is the small one. Okay, can you use your calculator to give me this time? This will be in seconds, and then I want you to change it into days. Do you need me to go back to the information on the slide, or do you have it? Right click back, or? Yeah, so that's the... Yeah. Can I... Do you need me... Which screen do you need up? Do you need the notepad or the slide? Kim? Which do you need up? Back here? Okay. back. This. Hmm? Well, you should probably got a big number, didn't you? Yeah, so I want you to convert it to days. It's currently seconds. Got it, Chad? Yeah? So, let me show you here. 2 pi square root, or, what's the or here? 385, wasn't it? 385000. Is that right? 385000 cubed over GM. GM. 5.97 10 to 24. Did you get this? You did? That's how many seconds there are. 2377913. Now, how many days is that? Okay, well, this is how many hours, and this is how many days. But that's not a surprise, because you know that the moon takes 1 month to go around the earth. This is the Muslim calendar, isn't it? Isn't it?
Yeah.
1 month is 1 lunar
Yes.
orbit, yeah. So, you know, you shouldn't be surprised by this answer. It's about 28 days, 4 weeks. Okay, continue. Right. I hope you can get this one. I want you to use the potential energy formula to tell me how much potential energy a satellite has. Now, just be careful with the English. This distance here is above the surface of the Earth. So in the picture, here's the Earth, here's the satellite. I've given you this distance. That's this distance. Okay? And I want to know what's the potential energy. And you cannot use MGH, because that only works when you're near the surface. So you have to use the other formula. You know, the minus G1. Okay? So, let's see if you can get it for me. It should only take you 1 minute, I hope. Say again? 100 kilogram satellite, yeah. Why, you think this is too small? Small satellite.
It's like 10 kg
Yeah. I don't actually know how big satellites are. I just said it was 100. You got an answer? Yeah? Yeah. So let's just type it in here. Minus G times M times M over R. And the R is 6371000 plus 35768 000. Oh, sorry, thank you, Matt, thank you. So the potential energy is pretty big negative number, which is not surprising because you need a lot of energy to free things which are trapped in Earth's orbit. This is why rockets are so big, you know. Okay, did you get that? Yep. Right, there's about 12-13 minutes left, so I think that's good enough to get you to try some of these. Yeah, and then we only have one lesson left for this chapter. So if you can try these for a few minutes, that would be great. I had one of these for breakfast, and you had one as well. The three of us had one. Now, you have, do you want to borrow my book, or is it okay for you to share as you're working on these? Is it okay? Yeah. So actually, Matt, the first one you can see, you can calculate how much force there is between 1 kilogram and 1 kilogram when they're 1 meter apart. Very healthy. Very healthy. Very healthy. Maybe this is the reason for the 90 kilograms. I know what I'll do. I'll help you. I'll help you by taking one. I'm helping you. Yes. Is this your lunch? Your breakfast? This is snack.
Yep.
Ooh, healthy lunch. Nice. You make it? Nice.
Some fruits.
So, it's funny. Healthy, unhealthy. It's balanced.
Balanced.
Yeah, balanced diet.